What is going on, everybody, and welcome to part 4 of the reinforcement learning series. In this video, what we're going to be doing is building our own Q learning environment. So the first thing I wanted to do when I learned Q learning, yes, it was useful to use the OpenAI gym environment, but the first thing I wanted to do is make my own environment. And I didn't really intend to make a tutorial out of it, but people were asking, and then it's kind of like, well, obviously that's what I wanted to do, so of course that's what other people probably want to do too. So anyway, here we are. Let's make our own environment. So I'm actually just going to kind of run through the environment that I made and explain it as I go. So we're just going to do the program linearly. But if you have questions, whatever, as always, comment below, join the discord.gg/Centex, and feel free to ask any questions. But it should be pretty self-explanatory. It's not a super complicated environment. And just in case, I guess I'll explain it a little bit before we get in. But so first of all, I love blobs. I use blobs for like examples of everything. So if you haven't noticed by now, I'm a blobophile. And anyway, so I always want to make blob things. And so the idea was to make blobs. And in this case, you've got a player blob, a food blob. That's the objective we're trying to achieve. And then just for, complexity, I added an enemy blob as well. So the idea is that you have this player blob, and we'll start by having the enemy and the food not move. It just stays stationary, and they just kind of initialize in random positions, and then the player blob has to move to get to that position. And then later we can add in movement. It's just that letting the things move is kind of irrelevant to the model learning how to actually move, except in one example, which is so if the enemy is moving and you're moving, you could in theory move into each other. If the enemy is not moving in training, you might learn that it's totally fine to get close to the enemy as long as you don't hit the enemy. But if the enemy can also move, they could collide. But anyway, not really worried about that, but you guys can feel free to tinker with that. Anyway, let's get into it. So we're going to be using OpenCV. So the first thing that I want to do is open up a command prompt, and let's go ahead and pip install Python dash OpenCV. Let's make sure we have that. Is it OpenCV? It might be OpenCV dash Python. OpenCV dash Python. Okay, I feel like I always get that wrong. Anyway, okay, pip install OpenCV-Python. If for whatever reason Python-OpenCV did install for you, you probably just installed something really bad. So don't use it, get rid of it. Moving along. So, all right. So we are also going to use NumPy, but you should already have that. And then we're going to use the Python imaging library. And I want to say that would be a pip install pillow. This is a virtual machine and it should be clean, so if that's not what I want, we'll find out soon enough. But we'll grab pillow, and then to use pillow you import capital PIL. So that should be everything we need. Let's go ahead and import NumPy as NP. So we're going to use NumPy for the array types of stuff. From PIL we're going to import how to type image with a capital I. Import CV2. We're going to import matplotlib.pyplot as PLT. We're going to import pickle, and that's to save and load our QTable. Then we're going to, from matplotlib, we'll import style just to make our graph pretty, and we'll do style.use ggplot. And then finally, we'll import time. We're going to use time purely to set dynamic QTable file names. And so it has like some order. What's your deal? Probably too undefined. Oh, it's typoed style. Okay, great. So the first thing I'm going to do is just try to run this real quick. Make sure it actually runs. It does. Okay, so all our imports worked, and we're good to go. So now we're going to have some, oops, did I just delete? Totally did. Okay, so now we're going to start with some of our constants. So we're going to say size, and we'll say this is 10. So we're going to skip the whole make a huge environment and then boil it down to action or observation spaces, discrete observation spaces. I'm going to skip that step. I'm just going to make it a grid. So in this case, it's going to be a 10 by 10 grid. So the player, the food, and the enemy will be initialized at a random location on a 10 by 10. But we can change this as time goes on. I'll talk about how some of those changes will impact things, but it obviously, as you increase this size, especially depending on the size of your action space as well, that is going to just exponentially explode the number of possible combinations in your queue table. So anyway, we'll start with a 10 by 10. That should be pretty simple. How many episodes? So HM episodes, we'll say 25,000. We're going to say we're going to give a move underscore penalty. That's going to be a 1. An enemy underscore penalty. So this is if we hit the enemy. We're going to say is a 300. So we'll subtract that penalty basically. We're going to say a food reward 25. I haven't really decided where I want this. I don't know if I really want it to be 1, a 0 like we had with the mountain car, 25. I haven't really decided. I don't really know what's the best one to use. So I'm just going to throw in 25. I haven't noticed anything, huge to tell me one way or the other. Then we're going to have epsilon, lowercase, because it's going to change over time. We'll start at 0.9, another thing that we could change a ton. Eps decay, so it's epsilon decay, 0. I went with 998. And the way I came to this was I just made a for loop and I literally just decayed. So I just took epsilon times, for I in range, say 25,000, multiplied this, and I just kind of looked and I was like, okay, that looks good. So I literally just pulled that number out of nowhere. Moving along. Now we'll say show underscore every. So this is just like before. How often do we want to show? I'm going to say every 3,000 episodes. If I recall right, my environment is actually a little quicker than the mountain car one. Okay, show every 3,000. Okay, so now what we're going to say is start. We'll have a variable here, start queue table. And for now we'll say none, but then it could or file name. So if you happen to have an existing queue table that you want to load in and train from that point, you would throw that right in there. Now you might want to do this for a variety of reasons. You want to continue training, or at least we haven't really coded in a good way to decay epsilon to 0 and then train for a little bit and then reintroduce epsilon. We don't really have a good way to do that. So if you really wanted to do that, you could decay epsilon to 0 or train for a little bit as with very low or no epsilon, and then load it in, add epsilon, and continue. And I've actually found that works really well to decay epsilon, let it go for a little bit, and then set epsilon back to 0.9 or something and decay it again, and then let it train for a while and then decay again, and keep repeating that. That seems to actually learn pretty well. So anyway, for now it's none because we don't have a queue table, but if we had one, we just pass the file name. So now we'll throw in learning underscore rate. We're going to say 0.1. Discount, we'll set, again, 0.95. These two variables I really haven't played with much, so couldn't really tell you how it's going to impact things. But now that you know how to do analysis from the previous video, feel free to tinker with them. Now what I want to do is I'm going to give a player n equals 1. We're going to say food n. These are just numbers for labels in keys, rather, in a dictionary. That's it. So player n, food n, enemy n, 3. Again, it's just definitions for what number these things represent in a dictionary. So we're going to say D equals, and then we're going to have 1 colon something. Well, I'll just fill it in. So these will be the colors. So 255, 175, 0. Now, I'm actually defining these colors in BGR format, even though I was really trying to use RGB. So side project is, if anybody can tell me why is it BGR, because I don't think it's I don't know. Maybe I'll figure it out as we go, but that was a problem I haven't solved yet. Anyway, it's 255, 0. So the player, B, is mostly blue, some green, so it's kind of like a lightish blue. Food is BG, so full green, so the food is green. And then the enemy will be 0, 0, 255, so BGR, so maximum R, so it'll be very red. Cool. So, oh, you don't like that, huh? All right. I'm surprised it does. I'm surprised it's accepting my spacing over of the dictionary. I don't think that's PEP8. Maybe it is. It must be if it's accepting it. Okay, so now what we need is we need a blob class, because really all of these blobs are going to have a lot of the same attributes. At least they're going to need to be able to move. They're going to need a starting location, like they need to be initialized randomly. They're going to need to be able to be moved, and then later, basically our observation. I didn't really want to use, because you would have like a huge observation space if you needed to pass what is the location of, like, I felt like you'd have to, the problem would be much more complex, I guess, if you passed the physical location of everything. So my plan is instead the observation space is actually going to be the relative position of the food and then the relative position of the enemy to the player. That's going to be the observation. So to get that, we need to be able to perform some sort of operation that will produce that value. So anyway, we're going to make a blob class so that we can handle for that. I get asked all the time, hey, why don't you code in object-oriented programming all the time? And it's like, well, I just use it where it's actually useful. And in this case, it seems to me that making a blob class is actually useful. So anyway, class blob. So define our init method. And if you don't know object-oriented programming in Python, I would go to pythonprogramming.net, go to Python Fundamentals, Intermediate Python, and then in this series we get into object-oriented programming here. And I would strongly recommend you go through this if it's confusing to you. And then we also are going to do some operator overriding and stuff like that. So you might want to check that out if that's confusing to you. So our init method, this is just going to run immediately. So we're going to say self.x is going to be equal to numpy.random.randint between 0 and the size, all caps. And then we're going to do the same thing for self.y. So that'll just initialize randomly. It's going to cause a slight issue. So if, in one case, the player could spawn right on the food. That would be lame. The other one is the player could spawn right on the enemy. That would also be lame. And finally, the enemy could spawn on the food or the food on the enemy, whichever way you want to look at it, glass half full, half empty kind of thing. That kind of stinks that that's a possibility. I'm not going to handle for that because I don't really feel like writing the code for that. Define, we're going to make a string method. I'm not even sure. I use this for debugging purposes, but then I'm not even sure we need it now. But anyway, I'm going to return an f string of self.x, and then we'll just say comma self.y. So if we want to print the blob, it'll just print the blob's location. So now what we want to do is I'm going to override, define the subtraction operator here, I think it's operator overloading. Anyway, someone will correct me. Actually, it is. Anyway, return. So this just allows us to subtract a blob from another blob. So in fact, we need another blob. So I'm going to say other. So so when we subtract, when you do a minus and then a thing, that thing will get passed here. And then in here, we're going to say return. And in this case, what we're going to say is return, and then in parentheses, we're going to say self.x minus other.x, comma, self.y minus other.y. Cool. It looks like PEP8 doesn't care either way if you want a space here or not. I'm going to get rid of the spaces. Okay, so that's our subtraction operator overloading. I think it's operator overloading. I'm going to go with that. Now, I'm going to define, basically this blob needs to, the player is going to take a discrete action, right? So we're going to have an action method, but really the player is the only one that's going to use it. But there might be a time where you want to have many players. So I'm gonna go ahead and do this. Like in this, like Q learning, we're not going to have many players, I don't think. I can't really see a good reason why I would do that. But later we might want to do that. And then, so action will actually interact with another method. I'm just going to pass for now. And we're going to call this move method. And, you know, it'll be self. And then probably X and Y. And in fact, I'm going to set X and Y just default to false before I forget. Okay. So in action, we want to be able to pass a discrete value. So we'll say self choice. And then we're just going to say if choice equals 0. Now we're going to start taking some actions. So we're going to say self.move. And we're going to say x equals 1, y equals 1. So it's going to move 1 and 1. Now what I'm going to do is I'm just going to copy this, paste this, and this will be elif choice equals 1, and we're going to say -1 and -1, and then again we're just going to copy, paste, paste, set this to 2, set this to 3, and then -1 and 1, and then 1 and -1, and those are going to be all the choices possible. I wanted to do this just to keep the action space relatively small, but this means the player can only move diagonally. Now, if I had thought of this when I was coding this, I wouldn't have continued. I would have actually done each of... Sorry, I just punched the mic. I wouldn't have done that. I would have also added all of the X only and Y only movements as well, so it could move up and down. Because to me, I would not have expected Q-learning to be able to handle for this. But like I said, I actually made this environment before I actually thought I was going to show you guys this environment. So I already know it's going to work, and it works by using the wall. So if it gets to the wall and then tries to move diagonally, it moves up or down, right, or side to side, depending on which wall it's at. So it still actually works, and I'm still amazed that it learns to use the wall, because as you'll see, it has no idea about the wall. It doesn't know there's any boundary to its environment. So the fact that it learns to use the wall is fascinating, and I don't know if it's because it's not smart enough. It's not like deep learning where if it knows it's on evens or odds and then the food is on an odd, like let's say the X is even for the agent, and then you've got, like, you know what I'm saying? Like, it's that exact combination that like a deep learning model could figure out and be like, oh, we need to flip this, let's go to the wall. But for Q-learning, I don't think it should be able to learn that. Because this is not how it works, but it actually does work, and this model can be trained for like almost 100%, because like in theory, half of the time when it gets initialized randomly, the food should be in a location inaccessible without using the wall. But this model actually learns to succeed almost 100% of the time. So that's mind-boggling. But anyway, if you want to add more choices, go for it. I'm going to leave it this way, but just take note that it can only move diagonally, and it's amazing. So now let's code the move method. And basically we want to be able to move randomly if there's no value passed here, or move very specifically. So we're going to say if not X, then what we want to do is we're going to say self.x plus equals np.random.randint between -1 and 2. So it's from -1 up to 2. So that just means it will either do a -1, 0, or a 1. So keep in mind, it has the ability to do 0. So this random movement can move up or down. Fascinating. If not X, else self.x plus equals X. Then we want to do the exact same thing for the Y. So I'm actually just going to copy this, come down here, paste. So Y, 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 and Y. Why though? Okay, so now, so that's it. So that's handling for X and Y. The problem here now becomes when it hits the wall. So recall, our size is a 10. We're trying to make a 10 by 10 grid. So if the agent attempts to move beyond that, we need to thwart it. Same thing with the food if we allow the food to move. Spoiler alert, we'll turn on movement and you'll get to see it. Or at least I'll show you video of it. It'll take probably too long to do it, but you can train it on your own. So, okay, so if self.x is less than 0, because it could be at the 0 position, it just can't be less than 0. We're going to say self.x equals 0. No colon required there. If self.x is greater than the size minus 1, rather. So again, the size is 10, but the positions are 0 through 9. So there's 10 positions, but so that's why. So if it's greater than 9, we're actually at the 11th position. So we say size minus 1 there. Then what we're going to say is self.x equals size minus 1. We need to fix size there. Okay. Now we're going to do the exact same thing for y. So we'll say again y, and then we'll do y, y, and y. Fabulous. So now that should be everything we need for our blob class, which I will now refer to as blobjects, which you've all heard if you've seen any of my tutorials with blobs. So now what we want to do is either create the Q table or load the Q table. So what we're going to say here is if start Q table is none. So if we don't have the start Q table, we need to create one. So we're going to say Q underscore table equals a, we're going to just make it a dictionary. We could do like something similar to before, but we're going to do it different. So all we're going to say here is for I in range of negative size plus 1 to size. This needs to be all caps. Size. So again, negative size plus 1, because we need to shift. And then size, and we're not doing minus 1 here because all the ranges are always up 2, so we're not actually including the 10. So we're going to do that. Now what we're going to do is do this 3 more times. So we've got 1, 2, 3. Okay, because we need every, so think of it this way, we have 2 coordinates, right? So we have basically the observation space is going to be 2 coordinates, where the first one is going to be the delta to the food. So the relative difference, because we're going to subtract the blobs, right? We're going to subtract these 2 blobs from each other. So where we overrode here. So it's going to be the subtraction of the current player, the player to the food. So that's going to return 1 tuple of x and y values. And then the other one is going to be the difference or the subtraction or the delta of the player to the enemy. So that'll be another tuple. So that'll be xy. So it'll be like x1, y1, and then x2, y2. Okay. It'll look like that. That's our observation space. Now, to get every combination, we're going to iterate through them. So we've got I. Okay, we could also get fancy. We could say x1, y1, x2, y2. Okay, that might make a little more sense since I just showed that other example. So now we have every combination. We want to add every combination to our table here. So, so the way that we're going to do that is I'm going to look at my code because I want this. This is something I would I didn't say it. I would fudge up. Q table, and then for the table we're actually going to pass the tuple. So it'll be a tuple, and I changed my values, so I already kind of screwed myself here. Like this, right? So that's going to be, the key is a tuple of tuples. So we're going to say x1, y1, x2, y2, and let's fix this. Right, okay, cool. So that, we'll save that, okay. There you go, Pepe. Okay, so then Now we just need to initialize with random values. So we'll just initialize the same way pretty much as before. So that's going to be equal to, and then so basically each observation space needs four random values, because we have our action space is 4. We have 4 discrete actions. So we're going to say np.random.uniform, and I'm going to say -5 to 0, and then we're going to say for I in range 4. Cool. I think that's everything. Looks good. Make pep8 happy, except for the line limit. Petition to remove the line limit from pep8. There's just like so many times when the line limit is stupid, and it would be dumb to not exceed the line limit. Okay, so so we've got our queue-table values. That's it. Our queue-table is initialized. Now we're going to say else with open. We basically, well, we're going to do start queue-table, so it's that file name. Our B as F, we're going to say now queue-table equals pickle dot load F. So if we have one pre-trained, awesome, we'll load that. Or rather, if we don't have one pre-trained, fine, we'll make one. Otherwise, awesome, we'll load that. So then we just have our queue code or our training or whatever you want to call it to do. So we're going to say for episode in range of how many episodes do we want. We're going to say the player equals a blob, the food equals blob, and enemy equals a blob. Easy. Then we're going to say if episode modulo show every is equal to 0, we're going to say we're going to print an F string on number episode, just so we know kind of where we are, and then we're going to say the epsilon also, so we kind of know where we are epsilon wise. Then we are going to, let's just print one more. We're going to say show every episode, mean, and we're just going to display the mean episode reward. So we're going to say np.mean, and that's episode underscore rewards negative show every colon. I just don't recall making the episode rewards. I don't think we did. Oh, now it, I saw it show up initially. Anyway, episode underscore rewards. That's just going to be an empty list. Okay. And then the other thing we'll do is show equals true. Else we'll set show equals false. And this is just so we can actually display the thing. So now we're going to get to our actual, so that's for episode. Now what we want to say is episode underscore reward equals 0, because we started 0. And then for I in range, we'll say 200. These will be how many steps we take. I'm hard coding that. You could later add that as a parameter if you like. So the first thing is we need an observation. So we're going to say obs equals, and that's going to be player minus the food, comma, player minus the enemy. So that's our operator overloading in action. Then we're going to have our random movement stuff. So we're just going to say if np.random.random is greater than the epsilon. As long as that's the case, we're going to do a regular action. So we're going to say action equals np.argmax of the queue table at the location of our observation. Otherwise, if that's not the case, we're going to say else action equals np.random.randint between 0 and 4. Again, it's up to 4, so it's 0, 1, 2, or a 3. So now that we've got the action, we're ready to take the action. So we're going to say player.action, action. So we take that action, which based on the action passed, moves based on these things that we pass. And again, I just kind of wanted to separate these because sometimes like you might want to move a thing. Maybe that thing we want it to move more than one value for whatever reason. Like the movement and then the action to move, I think, should be separate. For this simple example, at the stage that we're at, maybe it's unnecessary, but I think it's good moving forward. Anyway, no one was complaining about that. And then what I'm going to do is I'm just going to say maybe later. We might want to say something like this, enemy.move and then food.move, right? You might want to let them move. That would complicate things. I think for training purposes, it's better to not let them move initially because that just like really complicates things, I think. Again, I haven't actually tested either way. I just initially thought no point, and then later we should be able to add movement, and the agent should be able to handle for that pretty well, except for the one case that I was explaining where what about, you know, in training, if the enemy can't move, it's okay to even like brush alongside the enemy. But if the enemy could move, you wouldn't want to take actions like that. It'd be too dangerous because it could move into us. So now what we're going to do is code for the actual reward process. So after we take our action, what was the result? So what we're going to say is if player.x equals enemy.x and player.y equals enemy.y, you done screwed up. Reward equals a negative enemy penalty. Remember the negative. Otherwise, your agent is going to love the enemy. Okay. So if that's the case, now we're going to say elif, because we're going to assume, like, we definitely don't want, we always want to avoid the enemy. So if the enemy is sitting on top of the food or something, we'd rather just avoid the enemy. So elif player.x equals food.x and player.y equals food.y. Then we're going to say reward equals, what was it, food reward? Yeah, food reward, all caps. Else, so if those aren't the case, reward equals negative move penalty. So I think it's -1. Great. Now to do our Q function, we need to be able to like move. We need to make a new observation based on the movement. So what we're going to say here is new underscore observation equals, because we've made the move. So when we took that action, now we've moved. So now we're going to come up here and say the new observation is equal to player minus food, player minus enemy, and yeah. And then after that move, we need to grab the max future Q, and that's equal to np dot the max value of Q table for the new observation. So that gives us the maximum future Q, and then the current Q is equal to our Q table at observation and the action that we took, because it won't necessarily always be the maximum or the argmax or whatever. So okay, so current Q max, not argmax. Anyway, okay, so now we can actually calculate our Q. So so now what I would say is if reward is equal to food reward, then the new, so if reward equals food reward, new underscore Q is equal to food reward, because once we've achieved food, we're done. The same thing would be true if reward equals enemy penalty. If reward, That should be equals negative enemy penalty. If LF reward equals negative penalty, then we're going to say new Q equals negative. Don't forget that. I really badly want to make that mistake. Else, new Q will be the Q formula. So that'll be equals 1 minus the learning underscore rate. 1 minus the learning rate times the current Q plus the learning rate times parentheses reward plus the discount times the max future Q. Let's fix our PEP 8. Cool. So that's our new Q function. I'll zoom out, pause if you need to catch up. Okay, so once we've got that, we want to update the Q table. So we're going to say Q table at obs action equals whatever that new Q is. Okay, so at that point, we're actually done with the Q learning. Now what we want to do is show the environment if we want to show it. So because we kind of want to see it over time, and then also we want to track some of the metrics and then maybe graph or whatever as needed. So Q table obs action is a new Q. So the next thing is if show. Now we want to show it. Now we haven't even created the environment, but it's just a grid. So it's a pretty simple environment. So we're going to say the base environment is equal to np.zeros, and it's a, actually this will be a tuple here. It's a size by size, so a 10 by 10 by 3, because it's RGB data. And then we're going to say dtype equals np.uint8. So this is just basically 0 to 256, 0 to 256 by 3. So let's fix that. So now what we want to do is, so it's all zeros. So this would be an all black environment basically. And then we're just going to mark. So we're going to say env, and we're going to say food.x, food.y equals, and I'm just kind of thinking now, I think actually in, so in an array, it's actually y by x, I think, rather than x by xy, as we would traditionally think of xy, right? Because you've got your depth, then your width, basically. So I don't think in the environment, though, it's going to matter. Like, it's not going to make any difference whether we flip that or not, because one, it's a square, and two, we're just trying to visualize, so it would just be like rotated, I think, right? So I don't think it actually matters. It would only matter if we were allowing user input, but I actually think it makes better sense to say yx. I'll have to fix that in the tutorial, or the text-based version anyway. I think that's correct. I think it would be y then x in any array. Anyway, so we're going to say food y, food x equals the dictionary food n. So that's just our way of getting the color. Initially, I had a really great reason for that, but as long as we only have one food, it kind of doesn't really, you could just hard code this, or you could just say food color, so you could just say the food color is something. I had bigger plans for the dictionary, and then it changed. So anyway, that would probably make more sense, but just show must go on. So we've got food, then we have the player, so we're going to say player y, player x is the player n, and then this will be the enemy, move this mouse, enemy n, and then here will be enemy dot y, and then enemy dot x. Okay, so that'll change that grid's color. And by grid, it's really an image now. So it's an RGB image. So, but unfortunately, it's only a 10 by 10. So the next thing we're going to do is we're going to make this an actual image, and we're going to say image equals capital I image.from array, and then env, and then here's where I'm saying, hey, this is RG frickin' B, but for whatever reason, it doesn't care. It's BGR. And the way I found that out is I let the player moves and the food and the enemy doesn't move, and it's so clear. It's BGR. It's 100% BGR. It's crazy. Anyway, not env. It's env with a V. So that gives us our image. Now what we're going to say is image equals image.resize, and then we're just going to resize this to, you can pick anything you want. I'm going to say a 300 by 300, just so it's like I can see it. And then cv2.imShow, and then the title is whatever you want it to be, numpy array image, and then I'm going to throw in some kind of shoddy code here, but that's okay. Everybody accepts it. If reward is equal to the food reward, or the reward is equal to negative enemy penalty, this means the simulation ended and we really screwed up. So, so not if we didn't get the food, but if we got the food. No, we didn't screw up necessarily. If we got the food, yay, or we hit the enemy really bad. So if that's the case, I just wanted to pause it just for a moment longer. So I'm just going to say if cv2.wait key, and in this case it's 500 milliseconds, and then this little batch of awesomeness, oxff equals ord q. Basically, if you hit the q key, it breaks. I'm going to throw that in. And this is just how you let that CV2 window just refresh live, basically. So if we either made it to the food or we really screwed up by hitting the enemy, we want to run that. Otherwise, else, we'll just say wait key 1. So it's frame, and then at the very end, if we either get the food or this should be a double equals. Should not be an assignment. Yeah, okay. So the frames will go really, really quick unless we hit the enemy or get the food. And then it'll just hang there for a second just so we can catch it. Because this is 1 millisecond. So, well, it's not actually going to be 1 millisecond. It's going to take a little longer than that, but it's going to be quick. So, so that's our show. So now we can see the environment. Now what we're going to say is episode reward plus equals reward. And then if reward is equal to the food reward, or reward is equal to the negative enemy penalty, it's over. We break. And then finally in our episode loop, so just one tab over, we're going to say episode rewards dot append episode reward, and then we're going to decay the epsilon, so epsilon times equals our EPS decay. And then finally, we just want to graph things at the very end. So I'm going to say moving underscore average is equal to the numpy convolve episode rewards. So this will just create a moving average. And numpy ones show every, and then divide by show every. And then, is this mode? I don't even know. Let's tab that over. Yeah, mode is valid, and I believe that would be mode equals valid. So if you don't have enough to do the calculation, should you still do it or not? I'm pretty sure that's what that's going to be, but I could be wrong. Anyway, it's just a way for us to make a moving average. That's totally a Google operation there. because you want it to be like a rolling moving average. You could also do it in chunks like we did in the previous environment. I just think a moving average is a better idea. So anyway, there's a moving average, and then we're going to plt dot plot, and then for x, I'm just going to say I for I in range of the len of moving average. And then for our y, we will plot moving average. Beautiful. And then plt.y label, we're going to say reward, and then show every. So the moving average that we'll use is whatever the show every is. So if it's 100, if it's 1,000, whatever, it'll be 1,000 moving average and so on. plt.x label, we'll say this is our episode number. plt.show, and then finally with open, and then we'll make an f string, and we're going to say q table dash int value of time dot pickle with open that pickle comma wb as f pickle dot dump, and we'll dump our q table into f. Woo! Okay, coded that all the way through. How many reward? Food reward. Oh, so this should be lowercase lowercase reward. So what are the odds that I coded this without any other errors? I don't know. I don't know. We're going to find out, though. We are going to find out. Let's go into here. CMD Python. Whoops. Python Q Learning 4. Come on, baby. Okay, so it looks like we didn't do very well there. Do we have an error, or are we still making it? Warning, invalid. I think we're fine. Cool. Awesome. Show me my environment. Dang it. So yeah, this is your enemy. This is your food. This is your player. So it's running up. Oh, it looks like we got it that time. So if you see blue and red really quickly, that means we got to the food. If you see green and red, that means we ran into the enemy at the very end. So everything's happening sometimes very quickly. So we're only on episode, what, 9,000? Yeah, so whew, he's learning quick. He's doing pretty good. I forget how many episodes we said to go on. Probably 25,000, I think. Yeah, whew, he's moving fast. So anyway, the order that we drew things, the reason I made that order was so I could figure out what happens at the end. So these are all victories. So this is pretty cool to see. I'm just waiting for the end so we could load it in and I can show you guys, how we can start to kind of tinker with things. I also can bring up the text-based version of the tutorial for some other longer simulations as well. Okay, so here's our graph. We can see here we started these. This is basically the rolling average of our accuracy, or not really our accuracy, our rewards basically. Oh, we typoed reward. Anyway, cool. So you can see it definitely learned things really quickly, and again, half of the time. It should not be able to get there, but it uses the wall to get there, which is super cool. Okay, so what I'm going to do is close out of here. Guess I'll just... I had to save. Okay, so it saves our Q table. So as you can see, our Q table is like 13.6 megabytes. As we continue to train, because we're using pickle and a dictionary, that will expand over time, and you can actually use that expansion to know how many more random initialized values are being updated. Kind of an interesting outlook on my flaw of using a dictionary and pickling a dictionary as opposed to using NumPy correctly. Anyway, yeah. So what was I going to? Oh, so let's say we like what we think this is good. So then we could load in the Q table. So let me copy this, and then rather than none, we'll load in the Q table itself. So now we'll load this, and then now let's just set epsilon to 0. What else would I need to change? I'm trying to think. I think we're good, actually. Let's say show every one. I think that's everything. I'm probably missing something, but let's run it. Let's see how we look. So now you're seeing it play every time. He's doing really good. Get it, get it, get it. Oh, beautiful, beautiful. Again, more. Ah, solved. That's pretty cool. Okay, so ooh, I think he bounced around. So those where he's like bouncing around, that's a perfect example of the failure because he can't move. I say he. Oh man, these are so cool. But a lot of times you can see it actually go. It specifically, it could have gone straight there, but instead, or not really straight because it can only move diagonally, but it could like zigzag, right? But instead, it goes to the wall and bounces off the wall, and I just can't believe it's learned behavior like that. I just can't. It's crazy. But anyway, it has. So now what I want to do, let me break this. What was the other thing I wanted to show? Oh, let's turn movement on and see how we do there. So let me just do this. Whoops, this. Let's save that and then run it again. And so he died there. He's surviving now pretty well. I mean, he's catching so fast. That's just crazy. Died there once. Died again. Ouch. Anyway, yeah, I just think this is really cool. So I'm super happy that I made the environment, and I hope you guys are as impressed as I am with this. Because if I made a neural network that was like, say, a ConvNet, and it looked at this and it tried to make these learn to do this, it would take a while. And this trained in like, I don't even know, like what, 3 minutes? I mean, I just think that's pretty cool. I mean, I understand it's basic stuff, but I think it's really cool. So so now we could take things further, and like we could make a bigger environment. We could do more steps or whatever you want to do. And so feel free to tinker with the environment. The next thing, or the only other thing I want to show you guys is some of the results of using a much larger environment. So we're doing a 10 by 10. If you just change that to a 20 by 20, your Q table size goes from about 15 megabytes to like 250 megabytes, just for comparison's sake. And then if I figure out where the heck, I promise you there's some cool videos and photos. We just have to get to them. So let me see what this one is. This one's probably what we were just looking at. Yeah. And then I just showed how to get it live, how to get movement, blah, 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 blah. Nobody cares. Here. So here I start to actually train for a 20 by 20 space. So this is a 20 by 20 with no movement, I want to say. Yeah. So just seeing, could it actually learn a much larger environment? And obviously it does pretty well. And then I turned on movement for both the enemy and the food. Still no problem. And some of those are pretty complex where it's got to go around the enemy or deal with the enemy, which again is pretty cool that it can even do that. And I almost wonder if allowing movement makes it easier, because he's always trying to get toward he's always trying to get towards the food, and since the food is capable of moving in ones, like up, down, left, right, not just diagonally, that might actually even make it easier for the agent, let's say, rather than he. Okay, so that's our environment. I hope you guys enjoyed. If you've got questions, comments, concerns, whatever, you think I did something wrong, feel free to let me know. I didn't even think about, oh, it can only move diagonally. How is it actually getting food? Until I showed the code to Daniel, and he's like, oh, it can only move diagonally. How does it get the food like half of the time? And then I'm like, because I'm like, oh man, that's so cool. Because it uses the wall, but it has no idea about boundaries. Like, it doesn't know about the wall. So I have no idea why that works. Because again, it's just a cute, it's like brute force, right? It's just the fact that I just don't get it. I don't know how it could learn to use the wall, or if that's just random. Like if the wall being there, it's just random. Like it hasn't actually learned to use the wall. It just happens to hit the wall. You know, that could totally be the case. But anyway, yeah, that's pretty cool because that's pretty complex behavior. that I'm surprised it would learn. But anyway, pretty cool. It apparently does. So that's it. Yeah, like I said, questions, comments, whatever, feel free to leave them below. If you want to support the channel, you can click that blue join button, get some shout outs, get a special rank in the Discord channel, special channel to hang out in, and support me in the free education and all that kind of stuff. So check that out if you want. Otherwise, I will see you guys in the next video where we will be getting into, we'll probably be leaving basic Q learning behind and moving into DQNs or deep Q learning. So I will see you there.